Hi students, so in this lecture of Advanced Embedded Software Development, we're going to be talking about system programming and do a first discussion of what we mean when we talk about system programming, which is what we're going to focus on for the first third or so of this course. The learning objectives for today will be to introduce system programming, understand APIs and ABIs and the difference between the two, and also to introduce the POSIX standard. So what is system software? The book defines this as interfacing between the kernel and the C library. So common examples of system programming that you could find, it could be in a GUI, it could be a compiler, debugger, web server, or database. Really, there's a variety of software that could be considered system software. The book draws a distinction between system software and application software, in that application software might use higher level libraries, whereas what we're calling system software does not. So with system software, there's less details about the OS and hardware abstracted. And the reason we're going to focus on system software for this course is because we kind of want to get into the details. We're going to be working at the OS and kernel layer, and we're going to use that for the second third of this course where we start talking about programming in kernel land. So some of the cornerstones of system programming and how you do system programming. One is system calls, also known as syscalls, which is how you get into and out of the kernel for anything that deals with interaction with the kernel. A second is the C library, often used, a commonly used one is libc. And then the third cornerstone is the C compiler and linker, which is a part of the toolchain. So syscalls or system calls are kernel function invocations from user space. So this is something you can use to have the kernel do some piece of work for you, from your application. So read and write are examples of the type of things that would be a system call where the kernel would be doing some work for your user space application. There's roughly 300 of these system calls in total, and around 90% of those are implemented by all architectures. So in other words, the system call interface is pretty common across architectures. Different hardware architectures, that is. The second cornerstone is the C library, or in the case of GNU, it'd be libc or glibc. This is the wrapper for the system call, which gives you the ability to call from your C application. So the header file that you include, there's a function prototype that you call, and underneath that function prototype, there'll ultimately be a call to the syscall interface into the kernel. The third cornerstone, again, is the C compiler and linker in the toolchain, and we're going to focus on GCC and the GNU C compiler for this course. So one of the things that the book mentions is that it's not possible to link your user space application directly with the Linux kernel, and that's a design decision in terms of how the Linux operating system was designed. So for security and reliability reasons, it's better not to have a direct link between your user space application and the kernel. So instead, the way we get functions performed in the kernel space is to use what's called a trap. In a lot of cases, this is a software interrupt. So if you look at a simple hello world application that's doing a printf, that printf is going to be calling into the POSIX API library. And then the POSIX API library is going to be doing a trap that would invoke a kernel space function that would do something like print to the terminal in the case of printf. So how does the POSIX interface work? How is the interface between user space and the POSIX library defined? This is part of what's called an application programming interface. So an API is really just a definition about how one piece of software can talk to another piece of software. The software that provides the API is the implementation of the API definition. So the API is used to ensure source compatibility, meaning that you can write the source once, you can compile it for x86, you can compile it for ARM, any different architecture. As long as the source matches the API definition, it's going to be able to be recompiled and rerun on different platforms. So your source code can remain portable across hardware platforms and revisions. Ideally, there are some limitations on this. So we mentioned before that syscall has about 90% architecture similarities. So that means that there's approximately 10% of syscalls that might be architecture independent, and there might be some functions that you could call via an API that would be architecture specific. But for the most part, the APIs are going to be widely cross-platform and used across different architectures. So any of the common C library functions like printf, string copy, etc., you're going to be able to easily recompile for a different hardware platform and run without issue after you complete the compile and link. So to compare with the API, there's also what's called the ABI, or the application binary interface. And so this is talking about, where before we were talking about source compatibility, the ABI is talking about binary compatibility. So it's saying after you do your compile and your link step and you have an executable program, where is that program going to be able to run? That's what's ultimately defined by the application binary interface. So some of the things that's covered by the application binary interface would be calling conventions, byte ordering, or register use, meaning if you called some function, there would be some kind of convention about where the first argument would go in which register of a specific architecture. So it's kind of easy to see that that wouldn't be portable across different architectures. So for instance, x86 doesn't have the same register set that ARM would. So it makes sense that there would have to be a different ABI between those two different hardware architectures. So the API, or the ABI, is defined and implemented by the kernel and the tool chain. And the ABI is really defines the interaction with, defines a program's interaction with itself, with libraries, and with the kernel. So with itself, what I mean is when you call a function in your own program, that's going to use an ABI to decide, for instance, where to put the parameters that are passed into the function. So ultimately the ABI is going to be used to generate the binary that's the output of the compile and link step. And in order to know if your binary is going to run on a different platform, what you have to know is how close of a match do you have between the target that you originally compiled for and the target that you're trying to run on. And so some of the things that are going to impact whether an ABI is portable to a different platform would be obviously the hardware architecture, like I just mentioned, between ARM and x86, for instance. Likely those would not share a similar ABI. But there would also be software libraries. So whether you use glibc and also which version of glibc you used would be important. And the compiler would be important because that's part of the definition of how, for instance, the parameters would be passed in registers. So we talked about API definitions and APIs being defined. The API definition is one implementation of an API definition for user space is in what's called POSIX, which stands for the Portable Operating System Interface. It was started back in the late 1980s as a way to coalesce what the book calls the Unix wars. And if you look at some history of the Unix and Linux operating system, what you see is a chart like this, where there were several different, in the late 70s and early 80s, there were several different branches that developed where different versions of Unix originally and ultimately Linux were started, and each one of them were doing slightly different things in terms of API calls. And so there was a need, especially in the late 80s, as all these numbers of different Unix and Linux variants started to show up, there was a strong desire for programmers to coalesce how the API works and make sure that when you write software for one platform, you'll be able to recompile it and run it on a different platform without having to do custom API work per platform. So that was the original motivation behind the POSIX platform. And the Linux operating system that we're going to use as the subject of this course, you can actually go back here and click on this Google Groups link, and you can see the original posting to the Minix mailing list where Linus Torvalds proposed the Linux operating system. And this would have been in 1991. So this was around the time that the POSIX standard was starting to be defined, and everybody was working towards a common API that can be shared across all these different Unix and Linux variants. So the Open Software Foundation created what was called the Single Unix specification, and originally the IEEE POSIX specification cost money, but the Single Unix specification was free, and it ultimately incorporated the entire POSIX standard. So this was a big part of why POSIX was ultimately adopted, because it became part of the Single Unix specification. So POSIX is going to define the C code API for many of the concepts that we're going to cover throughout this semester. So file and directory operation, clocks and timers, semaphores, shared memory, threads. A large amount of what we'll be doing from user space is going to be defined by the POSIX API standard. There's an official list of headers you could find at this link, and there's lots of headers that you probably are familiar with and have used already. So for instance, standard IO, standard int.h, those are examples of files that are covered in the POSIX standard. So you've probably been using this already. You might not have realized that you were using POSIX.